So what does this order thing that I'm talking about mean? When I say lower order, you drop lower order terms. Lower order refers to how quickly a term grows. Um, and really what this means is as a number goes from being small, as your input keeps getting bigger and bigger, what part of the runtime or of the number of operations, what part of that function takes up the bulk of the contribution to how long the algorithm takes to run. And so our orders are actually probably a little bit used to this intuitively. So of course, the smallest thing is constant. And so that's the quickest thing to get dropped. Because no matter how big our input gets, this is always constant. So we have constant, which is just 1. Logarithmic, which is log n. Linear is n. Log linear, n log n. Polynomial is n to the c, where c is some constant. So n squared, n cubed, n to the 4th is polynomial. And finally, exponential is the highest order, and it's where you have some constant to the power of n. So like 2 to the n, or 5 to the n plus 1. And again, we can see if I see how I should best do this. So if I come here and I do, let's say I have a function f of x is x squared plus 2x plus 5 f of 10. So we can take a look over here on the left. Ignore the graph for a second here. Let's just focus on these numbers. So f of 10 has a value of 125. F of 100 has a value of 10,205. F of 10,000 gets really big. It's 100 million. Whoops, 100 million. And so notice that for f of 10,000, as 10,000 keeps getting bigger and bigger, the constant term here, which is the lowest order, contributes 5 out of 105 million. This middle term, 2x, contributes 2 times 10,000, so 20,000. So 20,000 out of 100 million. And x squared contributes 100 million. And so as the number keeps getting bigger and bigger, the x squared term is making up the bulk of our result. And so that's why we can kind of ignore these lower numbers, because the bigger f of x our input gets, let's say 10 million, right? 10 million is actually, f of 10 million is actually pretty close to just 10 million squared, right? 1 times 10 to the 14th compared to 1.00002 times 10 to the 14th. Those are super similar. So basically, with a very large input, this entire function, x squared plus 2x plus 5, is very similar to just x squared, the bigger that x gets. And so I show these on the right. All of these are examples of things that are of the given order. So if 1, 5, and 10 are all constant because there's no n involved. Log 2n, 3 log n, those are all examples of logarithmic functions. 4n, half n, just n, those are all linear, so on and so forth. In this class, for the most part, we're going to talk about constant. And we'll see code that takes constant time. We'll see code that takes linear time. And we'll see code that is polynomial. And most often, it'll be n squared. And maybe even higher. N cubed or n to the 4th. We can visualize these here. Something that's constant time, where on the x-axis here we have the number of operations. Sorry, the input size. And on the y-axis we have number of operations. Here we have constant, because regardless of their input size, on the x-axis, the number of operations is always the same. With a linear function, the bigger our input is, the more operations it takes in a linear fashion. So something that is twice as big takes twice as many operations. And quadratic is what you expect. So like going from 0 to 1 here goes up to around, close to 1. But going from 1 to 2, or 1 to 3, for example, it takes you all the way up to 4 operations. So here, the larger the input size is, the larger the number of operations that your code takes. But not linearly, but growing exponentially, so quadratically here, so n squared. Logarithmic is looks like this, and so in the beginning it grows pretty quickly, but then adding a bigger input actually takes less. It takes more time, but it's increasingly smaller, more steps, but more steps the further along out you get. And so you can see actually if we compare here, y equals n and y equals log n. I'll just move this over. Oops. +1. Yeah, I'll move this over just a bit so you can see. You can see here that log n is actually better than this one. Oops. Okay. I'll just do this. Move it over a little bit. So log n grows less quickly than linear. See on this graph on the right. So if our x-axis is the size of our input and the y-axis is the number of operations our program takes, we of course want a logarithmic program, with a logarithmic order of growth over a program with linear order of growth. Then on log n and exponential, I won't talk about those right now. But let's get to like some more practical examples here of how to get an order of growth. So I mentioned to get the order of growth, you take the number of operations, if you counted them directly, and you drop the constants in the multiplicative factors. So that's because, again, we want to focus on the dominant term. So here's our first number of operations. If I gave you some code and you calculated that this is the number of operations it takes by counting each operation, take a minute and think here for 5 seconds before I give you the answer. What would be the order of growth of this very first function here? So we drop constants and multiplicative factors. So what are the constants here? Well, and actually I should be really precise here, and not constants, but lower order terms and multiplicative factors, to be very precise. So what are our lower order terms here? Well, our highest order term is n squared. And we know that because n squared is a higher order term than n, and n is a higher order term than a constant. And so we are only going to keep the highest order term here, just 2n squared. And then we drop the multiplicative factor of 2 to get big O of n squared. What about this next one? So 10 to the 1000 plus 10n cubed plus 100n. Again, first we're going to keep only the thing with the highest order term. So the highest order term here is 10 to the, well, actually, you tell me, what is the highest order term? So 10 to the 1000 is not in terms of n, right? So this is actually a constant term. Even though it's very large, it is a constant. And so the largest order term here is n cubed. N cubed is a larger order term than n squared, which is a larger order term than n to the first. And so we get 10n to the third when we drop the lower order terms. And then we drop the multiplicative factors and we get big O of n cubed. So this is the order of growth. This is the big O runtime complexity of an algorithm that has this many operations in terms of n. Then for this next one, we have the same thing. So n is a higher order term than a constant or log n. And so just n, and we get big O of n as our runtime complexity. How about down here? What do you think? Well, if we multiply these out, the lower order term here, so this term has order kind of 1, right? This is n to the first. Over here, this is n log n times 0.0001. And so this is actually the higher order term because n log n is larger or grows more quickly than n. And so we drop the lower order term and then we drop the constant multiplicative factor and we get big O of n log n for our complexity. Finally, we have 2n to the 30th plus 3n. So which of these is higher order complexity? Well, if we go back on our slides, we were comparing n to the 30th to c to the n, to some 2 to the something, I think. So exponential is the larger higher order of complexity. And so if we go back to our example here, 3 to the n grows more quickly than n to the 30th. Even though n to the 30th seems really big, 3 to the n actually grows much more quickly. And so for a very large n, this will dominate the number of operations we have. And so we drop 2n to the 30th, and we get big O of 3 to the n for our order of growth. So to summarize this order of growth bit, the order of growth of our program is looking at the largest factor in the runtime, which the runtime we've been looking at as the number of operations it takes for a program to run. And so that means that that term in the function for the number of operations that occur for this particular function just dominates when n gets really large, when the input is really large. And the really handy thing here is that this doesn't have to be precise. This is why it's an order of growth. 3n and n and 2n and half n are all linear. So we actually don't care about how many operations happen inside of our for loop as long as they're all constant time. As long as they don't depend on the input, like something that happens n times or half n times or 2n times, it's all just big O of n, which is really handy. It's easier to think about. And so this satisfies what we wanted, where we want to think about a program's efficiency when the input gets really big. We want to think about how that runtime grows as input size grows. And we get an upper bound on our growth, which is great. We're getting an upper bound on the growth of our function as a function of the input size.